So let us have a look at some examples. Examples of real vector spaces. Real vector spaces. So what are the examples? So some familiar examples would be some familiar examples. So basically R the real vector space, and if you take any Rn or n greater than or equal to 2, these are all real vector spaces. If you take the set of all square matrices of order n cross n over R having entries in R, so these are all real vector spaces. If you take any if you take the polynomials having coefficients in R, this is also a real vector space, right? So the polynomial space is a matrix space, right? So these are Euclidean spaces. So these are quite familiar examples of real vector spaces, and likewise you can also define the counterpart of complex examples, that means complex vector spaces, which are so for complex vector spaces we would have C, Cn, right? We take the set of all matrices over C having entries in the complex field, the matrix space over C. Suppose you take the polynomials having entries in C, so the polynomial space over C. Okay. So these are all complex vector spaces. Okay. So what is our motive? So our motive is, so what shall I do here is that we are going to enlarge a real vector space into complex vector spaces. Okay. So I am going to enlarge it up to the complex field, right? So what we do, we are just enlarging the field. Which is, so what is the underlying field of a real vector space? So they are real numbers. So we are going to enlarge it to C, so that the vector space will remain same, but the scalar multiplication has been enlarged to from real case to complex case. Right? So you are going to scale any vector. So previously you have done it for real vector, real scalars, but now you are going to execute your scalar multiplication by means of complex numbers. Okay. So that is what sort of thing that we are going to do here. বোঝা গেছে মানে মোটিভটা বোঝা গেছে ঠিক আছে এবারে হয়তো অনেকে বলতে পারে যে why you are going to complexify real vector space আমরা কেন এটা করতে চাইছি তার তো একটা কারণ থাকবে তাই না হঠাৎ করে রিয়েল ভেক্টর স্পেস থেকে কমপ্লেক্স ভেক্টর স্পেসে আমি একটা নিয়ে যেতে চাইছি কেন হয় okay so there must be some benefits of this procedure, right? So maybe one can ask why we want to complexify a real vector space. Okay, the most basic reason behind this notion of complexification of a real vector space is that to solve differential equations which has been set for the real case, but if you enlarge that field to complex field, you will get benefit out of it. Okay. More convenience, more powerful tools that you will have from the complex analysis from the complex field, which is not there for real case. Okay. Okay. So firstly, we can say that to solve differential equations. Rather, one can say, rather equations by and large. Okay. So that means so if you want to prove any result for the real case, suppose you take any linear equations, right? System of linear differential equations. Uh, these coefficients have been taken on the field of reals. Then what to do? And sometimes it is very much convenient to you if you can change that equation. If you can change that equation to the complex field to get a complex solution space, some solution in the complex field, right? Then we try to use our knowledge on the complex field to get information about the real solutions. Okay? মানে আমরা যেটা করতে চাইছি আমরা মানে ব্যাপারটা হচ্ছে এরকম ধরো আমি একতলায় রয়েছি, ঠিক আছে, তো একতলা থেকে একটা ঘটনাকে আমি দেখতে পাচ্ছি না, তো আমি কি করলাম, আমি ছাদে গেলাম, ছাদে গিয়ে আমি চারিদিকে দেখছি, হ্যাঁ এই তো এই ঘটনা ঘটছে, এই ব্যাপারটা অনেকটা ক্লিয়ার হয়ে যাচ্ছে আমার। এইবার আমি ওই আমার ভিউ পয়েন্ট থেকে আমি এবার নিচে থেকে কি দেখতে পেতে পারি তার একটা আইডিয়া আমি নিচ্ছি। তো দ্যাট ইজ হোয়াট উই আর ডুইং। বোঝা গেছে? শোনা যাচ্ছে তো? হ্যালো, এই শোনা যাচ্ছে তো?
হ্যাঁ স্যার।
ওকে, মানে সারা শব্দ দিও, নাহলে বুঝতে পারছি না। Okay. That means suppose so এক সেকেন্ড, হ্যাঁ স্ক্রিনটা so okay. So we want to know. So we want to know if a subspace, if a subspace of Cn, right? So these are unitary spaces, right? Unitary space. So a subspace of Cn, uh, the subspace of Cn is going to be the solution space will be a solution space to a given complex to a given system of complex linear equations. Okay, is also the solution set for solution set to a system of real linear equations. Right? Real linear equations. ওকে, তার মানেটা যেটা আমরা দেখতে পাচ্ছি যে so we want to describe the subspaces. Okay, if we can complexify a real vector space, then that will become a complex vector space. Then we are going to explain what does it mean by subspace on that complex vector space to get knowledge on the real counterpart. এটা আমরা দেখতে যাচ্ছি and we can use different ways to complexify a real vector space. Okay. So let me start. Suppose I'm going to give you some examples also. So what is the definition? So suppose, so let us start by considering a real vector space. Suppose is V. Okay, is a vector space over the field of areas. Okay, so that means here the scalar multiplication has been given by the field of reals, right? That means if you take any, so you take for all lambda belongs to R, for all V belongs to capital V, so lambda comma V, this is lambda, right? So this is a scalar multiplication that is we are using here for real vector space. But what is our goal? We would like to impose a meaning of, we would like to impose something to define scalar multiplication of the same set V with respect to complex numbers. Okay, so we would like to define, we'd like to give a meaning of the scalar multiplication with respect to the field of complex. See, that is for any complex number, let us call it uh, lambda c, lambda be a complex number having representation a plus ib, and for in v belongs to capital V, we need to define what one does mean by lambda c v lambda c. Okay. What about it? So that is our requirement that we need to define the scalar multiplication of the vectors of the real vector space V by means of complex numbers. So that means if you can done, then you are getting benefit out of it because you are enlarging your field from real field to complex field. So what should I get if you can define? Suppose you can define this scalar multiplication. Okay? Then it must be like this. So if we would have defined it over C, then one might get what you get lambda C V. So that means what is lambda C? Lambda C is here A plus IB, right? So A plus IB V, and so therefore, so you like to have this is AV plus IBV. Am I correct? Okay. Now here you have a meaning of this because this A is a real number, right? This is a real number, and you have already considered the space, vector space over the field of V. So you have the definition of the scalar multiplication of any element of V by a real scalar, right? But you don't have the definition of this one, right? So you don't have this. Okay. You have the definition of this one AV, but you don't have this IVP, right? So that means multiplying by I, it has no meaning right now, but we would like to have. Okay. Okay. So one can say that. So here IBV does not have any meaning right now. Right? That means multiplying the elements of the vector space V by I, that is composite 12. So that is multiplying the elements of V by I has no meaning right now. Okay. But we would like to define it, right? Okay. So what you can do here, we are just keeping apart this I, and if you look at this case again by means of the ordered pair, so one can view lambda CV as like this, FV comma CV, right? In terms of ordered pair, right? Now this has a meaning because you have this scalar multiplication of V by the real scalar A. You have the definition of the scalar multiplication of V by means of the real scalar V, right? So you have these two quantities according to the definition of scalar multiplication by the real field to that vector space, because it is a real vector space as it comes. So we are going to define. So in view of, we are just taking out this this one, uh, and we are going to define it. So the definition will be the complexification. The complexification of a real vector space W, right? V is defined to be what we can do here. So the complexification of a real vector space V. So what do you mean by complexity? We are just taking the direct product, direct sum. I'm sorry, the direct sum. So defined to be the direct sum. Just look at this one. V plus V. I'm just taking the direct product, okay, of V with itself, or you can say direct sum of V with V. Okay, equipped with multiplication, equipped with the multiplication, scalar multiplication. So what would be the scalar multiplication here? So for all lambda plus 2, C for all, suppose we've taken small v, so here small v means, so it is a direct sum, so you are taking some P1, P2, plus 2 this. Right? So we are going to create a scalar multiplication, so it is lambda v. So what does it mean? So lambda v means, suppose A plus IB is the expression of lambda, and you are taking it as a direct sum, so V1, V2, okay? So therefore, what we do here, I'm just multiplying. So the definition is A V1 minus B V2 B V1 plus A V2. Okay. What is the idea coming out here? So that is, it corresponds to this one. Let me check. So if you take this matrix, This matrix is actually the complex number a plus I, right? And look at this one. A B1 minus B2 B B1 plus B2. Is it okay? We are just taking the complex number lambda. So here where lambda is a plus ib, or you can represent it by a minus b. Okay. এটা কি তোমরা করেছো? মানে একটা কমপ্লেক্স নাম্বারকে এই ম্যাট্রিক্সের মতো দেখতে এরকম একটা জিনিস দিয়ে লেখা যেতে পারে।
হ্যাঁ স্যার, ফার্স্ট আমার পড়িয়েছিলেন প্রথম দিকে কমপ্লেক্সের শুরুতে।
আমি বলেছিলাম বলে না?
হ্যাঁ হ্যাঁ, বলেছেন।
ব্যাপারটা আইডিয়াটা ক্লিয়ার হয়ে গেল। You are considering each element of BC as a column vector, right? V plus V, direct sum. So that means you are taking it as a column vector. Okay? And look at this multiplication. I'm going to define right? Like this. Okay. So this is nothing but actually we are identifying the multiplication law as we have defined the multiplication of two complex numbers. Now here you have a complex number lambda, and if you think V in terms of complex representation, that means what we have used here, just look at this. This V1, V2, and we write it here. So it is actually but if you look at this connect is always column vector, right? And also you can connect this B in terms of complex representation. This is V1 plus I V2. I'm not to say that these V1, V2, these are complex, these are real numbers. No? I'm just taking the complex representation of this entity. Okay. That means suppose you have two objects A and B, and you are taking the complex representation. That means A plus I, right? Or A comma B, ordered pair, or the column vector A, right? Whatever A and B are, but we are just taking the representation. We are thinking of this like this representation. Then you can easily handle this situation just by using this matrix A minus B B A B1 B2, and you will get that multiplication definition operation, right? Is it okay? And if you think of this multiplication in terms of this complex representation, you can easily evaluate. So for example, suppose you want to multiply an element of BC. Okay, so for example, let B is B1, B2. Then what would be IV? So what is I? So I is 0 plus I1, right? And B is suppose B1, B2. Okay. So what would be the matrix here? So 0 minus 1, 1, 0. And we are taking it as a column. Then what would be the resulting vector? So this is 0 V1 minus V2, so it is minus V2 and this is V1. So that means it is minus v2 comma v1. Okay. So multiplying any vector with I, it changes to this one. Okay. Okay. Now we need to check that. So one needs to check that. So what should be checked here? So your set is VC. So this is your set, which is the direct sum of you itself, equipped with vector addition. What is the vector addition here? The simple addition that has been defined over V, because V plus is an abelian group. Okay? So that means you are taking any two vectors. Suppose you take keep with suppose V plus V dash. So what should be the definition here? Here V is suppose V1 V2 and this V1 dash V2 dash. So what would be the definition? Just component wise addition, right? Yeah. And so this is your vector addition, right? And what is the scalar multiplication? It has been defined above. So for all lambda belongs to C and for all V belongs to capital PC. So here lambda 3 is defined to be the matrix. Okay. So let me call it m lambda V. That means m lambda V1. So what is m lambda? So where m lambda is a matrix corresponding to lambda. That is, if lambda is a plus ib, then m lambda must be a minus bp. Okay. Now it is okay. So one needs to check that we form a vector space. We form a complex vector space. That is a very important. Complex vector space. Okay. Okay. So now, so note that, observe that for a vector V, suppose V1, V2 belongs to VC, VC, what you can do? So here, so V, V1, V2, you can represent it by V1, comma 0 plus 0, comma 2, right? Am I correct? Now, note that. Suppose you take this scalar I, and you are going to multiply this I with the vector v2 comma 0. Then what will happen here? So that means 0, minus 1, 1, 0, and here it is v2 comma 0. Right? This 0 is the this 0 is a vector 0 in V, right? In V, real vector field. Then what is your resulting vector here? It is 0 into V2, this is 0. Very good. And this is V2. Okay, very good. So that means it is 0 comma V. So I V0, I V2 comma 0 has been transferred to 0 comma V. So therefore, V, which has been represented in terms of the V1 V2 and has been split off, is, but in view of the above multiplication with respect to I, this V1 comma 0 will be written as I V2 comma 0. Okay, right? So formally, that's the elements. What sort of the things is this? So it can identify this element by V1. You can identify this element by V2 as an element of V. And you can represent this V as V2 plus I. Is it okay? Yeah. Here this multiplication, so this maybe seems to you that it does not have any meaning, but we are actually thinking of this I V2 as I V2 comma 0, which is 0 comma. Right? So thus the elements, thus elements of PC will formally look like E1 plus I, right? Okay, where E1 V2 belongs to. Okay. Are you getting my point? So what sort of things that we have done here, we have already seen whenever we have defined C complex number field, right, out of the real field. Just think of it, what we have done. So let us recall that we have considered C as a set of all ordered pairs, right? Equipped with two operations, which are, what was the operations that has been defined in C? So first of all, the addition, which was as before component wise, right? A plus C, B plus C, which is known to all. And the scalar multiplication, which is AB dot CD, which is actually A2 minus BB, AB plus this. Okay? And in terms of these two operations, C has formed a field. But just look at the representation of C, any members of C. So we have we have written I as element 0 comma 1, right? 0 comma 1, right? And we look at this case and we can identify any real number, any real number a with a member of C, which is a comma g. That is, a has been identified. A comma g is a real number, right? So every real number identified with a dim C, which is looking like a comma g. And also, if you want to multiply this kind of members of C by I, by definition, what would be your what would be the case here? The I means in view of these that means right? Uh, so what is the case there? So AC, so your A means this, AC minus BD, so it means it is 0, and we have AD 0 plus BC, so that means it is A. So here, so 0 comma A means I, A comma 0. Okay. So this is true for all real numbers. So hence, what we have done, so any AB can be written as A comma 0, 0 comma B. So here A comma 0 plus, so 0 comma B can be written as in terms of this, so here I, B comma 0. So look at this case, so this is identified with A, this has been identified with B, and this is your I. So that means any member of C can be represented in terms of A plus IP. So what we have done, we are taking the direct sum. So that means C has been taken as R equal to it. So let's look at this case. So equal to it, the vector addition. What is the vector addition? So take a vector here, so E plus CD, it is A plus C, B plus D component wise. And what is that scalar multiplication? So taking any lambda, and taking any member from, so lambda is also a complex number, right? For all lambda belongs to C, I am taking complex numbers. Okay. Okay. So lambda AB can be written as, so lambda. Let me just take this as CD. Okay. So lambda has been chosen to be the number AB, and this is your CD, right? And what has been done for the complexification? We are taking the matrix M lambda. So what is the M lambda here? With respect to this AB, what is your M lambda? So it is A plus BA, and we have taken this CD as a column vector. And what should be the definition here? So this is AC minus BD, and this is AB plus BC. Great. So that means what is happening here? This is nothing but the complex multiplication that has been defined in the field of complex, right? So this is nothing but this is the multiplication of complex numbers. So we can view the complex vector space C as a complexification of the real vector space what R, right? So C as a vector space over C is nothing but a complexification of the real vector space R over R. Is it okay? দেখো বোঝা গেল কিনা? Okay, so that is hence hence the complexification of R RC, this is isomorphic with what? The C vector space. C. Okay. So this is a very nice example, although we have done it in our preliminary study, but we have not seen it in this way. And this idea has been generalized to any real vector space V, and you can complexify this vector space V just by making an agreement that what would be the scalar multiplication of any vector of this form if you take two elements from V, that is A, V1 and V2, and you want to set up a definition of a scalar multiplication, which is suppose you take any complex number lambda and you take any vector V, which is something like this one. So this is nothing. If you regard the complex number as a matrix, and if you look at the member of that BC as a column vector V1, V2, then you can make an agreement that that multiplication must be same if you take that matrix and that column vector, and if you take the matrix multiplication. Okay. So other examples might be like this. So, so what would be the so the complexification? Suppose you take Rn, right? So the Euclidean spaces, the Euclidean spaces Rn, okay, will have the complexifications. Complexifications which are isomorphic. What? If the complexification of R is isomorphic to complex vector space C, then the complexification of Rn will be isomorphic to the complex vector space to the unitary spaces, right? Unitary spaces. Yes. So by looking at this Cn as the direct sum of Rn is Rn equals to its usual addition and scalar multiplication which has been defined. That has been defined. Okay? Is it okay? So what is the complexification of MNR? Complexification of MNR, real vector space MNR. What is the complexification of MNR? Is isomorphic to MNR, direct sum with MNR equals to its usual addition and the complexified scalar multiplication, which has been defined above. That means if you take anything after so that is which is so that is you take any lambda and you came to matrices here, right? So suppose your lambda is A minus B, BC, and if you regard this object AB as column vector AB, then it is nothing but, so it would be A B minus B capital B, and this is BA plus A. So that means AA minus BB, comma BA plus, okay. So in terms of this, you can check that is so in the complexification. So that is the complexification MNR C. What is that? This is isomorphic to MNCH. So which is MNR dx MNC. MNR. Okay. Okay. Similarly, the complexification of the polynomial space, real polynomial space, Rx is isomorphic to Cx. Cx, okay, which is Rx dx sum with Rx. Okay. So elements of any uh, f Cx, that means any polynomial in Cx can be regarded as this one. Okay. In terms of this, you can say that the complexification of the real polynomial space Rx is actually Cx. Okay. Great. Note that, note that the above examples tells us tell us a nice observation, which is which is every which is the identification, the complexification the complexifications of Rn, MNR or Rx, the complexifications of Rn, MNR or Rx will transfer a real basis of the respective spaces real basis of the respective spaces. The respective spaces through a complex basis. Complex basis of their complexifications, of their respective complexifications. Which are respectively sphere, MNC, or series. Okay? Okay. So let me prove it for in general. So now let us have a look on that. For a general case. Theorem that let P be a non-zero real vector space. Okay? And non-zero real vector space and only VR is a real basis of it. Okay? Then the conclusion is then the set of the BC which is actually the set of all members of this form E comma 0 and E belongs to curly will be a complex basis of the complexification this of V. Okay? So what will be the proof? What will be the proof? Suppose V equals to V1 V2 equals to VC. Any vector. VC. So now this V1 and V2, these are all members. These are members of a real vector space V. So being a member of V, it can represent V1 as, because we have already considered this Br, early Br, as a real basis of V, right? So that means we can represent this V1 as a linear combinations of the members of, say, suppose summation lambda I ei or here. Lambda i's arguments. Okay. Similarly, you can represent it as some mu j, ej onto m, or mu j1 arguments, and ei is both. So these are all members of family Br. So where ei's, ej's are members of family Br. Right? Okay. So therefore, what we will have, so V is V1 comma V2, so therefore it is V1 comma 0 0 comma V2, right? I'm just uh, putting the expression of V1 and V2 here. The summation lambda ei from 0 plus 0 summation mu j ej. Okay. So therefore it is, so summation lambda i's ei comma 0 plus mu j's 0 comma x. So there is this V concept to V. So this is, this implies, so V can be represented as a R linear combinations of the vectors like ei comma zeros and 0 comma ez's. R linear. So why it is R linear? Because these scalars are real numbers. So that is why there this representation is a R linear combination of ei comma zeros and 0 comma ez's. Okay, but we have already seen that, but note that, recall that any element of this form 0 comma ej, recall that 0 comma ej is nothing but it is the scalar multiplication of the vector ej comma 0 with r, right? Okay, and since you can write down this vector 0 comma ej as I times of ej comma 0, so ultimately the expression that has been coming out here is actually a complex linear combination right now, right? Okay. Okay, so therefore this says that the above expression for V sounds out to be a C linear combination of, because right now this I has been multiplied with these new j's, right? So ultimately, the scalars will be, as a whole, it will be real, it will be complex numbers, right? Although lambda I, these are reals, but in general, these are complex numbers because of this i's, right? That will be coming out from each vector in this summation. Okay? So therefore, C linear combination of the vectors ek comma g zeros, or ek's are a I. Am I correct? Okay. So therefore, we can say that therefore the set only BC, which is actually the set consisting of these kind of vectors e comma 0, but e has been chosen from here. So therefore the set is response BC. So it remains to check that whether this curly BC will be linearly independent over the field of complex in BC. Okay. Okay. So now if we check that curly BC is linearly dependent in VC over C, we assume that suppose we take any finite any vectors taken from BC, okay, and let us choose finite scalars, the same number of scalars which equates with the number of vectors we are choosing from finite BC, right? So that means lambda C1, and this is let me EI1 comma 0, lambda C2 EI2 comma 0 plus lambda CA EI2 comma 0. Suppose it is 0, 0. Okay. So our motive is to prove that lambda C1, lambda C2, lambda CK, these are all 0. Okay. Okay. So now you can represent this lambda C1 as A1 plus IB1 EI1 comma 0 plus next will be A2 plus IB2, and this is EI2 comma 0 AK plus IBK EIK comma 0 is going to be 0. Now in terms of the complexified scalar multiplication, so what would be the situation here? So if you take the multiplication here, so what is that? What is that? So this is A1 EI1, right? Minus B1 0, that is 0, comma A1 into 0 plus B1 EI1. So it is B1 EI1. Okay? So you can easily compute the next scalar multiplications. So it is A2 EI2 B2 EI2, and the last one is AK EIK BK. So therefore A1 EI1 plus A2 EIK plus AKIK, comma B1 EI1 B2. So this is 0, right? So therefore each of the component will be 0. So summation AI summation A P EIP, it is 0, P runs over 1 to K, and also summation B L EIL is also 0. EP EP EIP P runs over 1 to K. Okay? Now see this EIP, these EIPs are members of curly BR, which is already has been considered to be a basis of V. And this implies, so this implies all these scalars APs are 0, BPs are 0 for all P runs over 1, since it is a real basis in V. Okay. So all these scalars APs are all 0. So hence lambda C1, lambda C2, lambda Ck, all these are which proves that curly BC will form a complex basis on PC. Okay? Okay? Is it good? Is it okay? So one might have this the corollaries. The corollary one will be, suppose you take any zero vector space, right? Only it will be claiming the zero vector. Then what will be its complexification? Its complexification will also be zero. Right? So if V is a zero vector, then its complexification this is also zero. Right? So there is no other choice. Over 2, suppose we are having a real vector space with finite dimension. Okay? Then what would be the dimension of its complexification? What would be the dimension? So if V be a finite dimensional real vector space, then its complexification VC is also finite dimensional and finite dimensional over C, and not only that, the dimension of VC over C is equal to the dimension of V over R. Okay, so the dimension does not change. Although you are enlarging your field, but the dimension remains same because it is the complexification of the real vector space. Okay, and we have proved it in this theorem that any real basis can be transferred to a complex basis just by means of just taking the embedding, right? E goes to E comma 0. This embedding works here, right? So E goes to E comma 0, right? So E goes to E comma 0. So this is the embedding actually. This is, from V to PC, right? This is actually G dx. So this is embedding. This embedding works here. So you are choosing if you have a finite dimensional real vector space, then its complexification will be also finite dimensional, having the same dimension as that of the real vector space. Why it is so? Because of this embedding, and you can transfer any real basis of V to a complex basis, which is just using this, which will be coming out just by using this embedding. BR goes to BC, which is nothing but the vectors of that basis will be of this form, ordered pair E comma 0, where E is in the real basis. Right? Okay. Okay. So yeah. Okay. Now one thing that you have seen, or you might get interested on that it should be observed that we have already seen that the complexification of a real vector space R, right, was the complex vector space C. I have proved it. The complexification of the real vector space R is actually isomorphic to the complex vector space C. That means C over C. R over R will have the complexification C over C, not C over R. Okay, so that you might be confused sometimes. Okay, so complexification. So the complexification R over R. So this is actually C over C. C over C, not C over R. Okay. Okay. Because why? Why it is so? Because of the, you can check it just by using the above theorem. Okay, so you can write, so since, so we regard the field of complex numbers C as a real vector space. Okay, and then you see that its complexification. What would be its complexification? Just representing it in terms of the real notation C C. This is the complexification of the real vector space C. Okay, so its complexification should have the complex dimension, right? Complex dimension 2, since why? The dimension of C over R is 2. Just by using the above theorem. I'm just using it. Just look at this. Dimension of V over R is the dimension of the complexification VC over C. So I'm just taking C as a real vector space. The dimension of C over R is 2. So therefore its complexification over C has been of dimension 2. Is it okay? So so look at look at elements of C C. So what are the elements? You can view this C as C direct sum with C. Okay? Equal to the usual addition. So equal to the usual addition and the complexifier square multiplication, which is what is that? So you take any lambda, and if you take any v, okay, so that means lambda can be written as a complex number a plus ib, and v is nothing but v1 2 where is v1 v2 both are complex numbers. Okay, and using the same procedure as above, this so you can write down it's a v1 minus b v2 b v1 plus a v2. So this is the complexified scalar multiplication, and with respect to this CC will form a complex vector space, which is the complexification of the real vector space C. Right? Okay. Okay. So this tells us that. So this says that this shows that the complexification of the real vector space C. Now we are looking at C as a real vector space, and we are considering its complexification. But it should have dimension 2, right? So therefore, the complexification of this real vector space is not the field of complex, as because why? as because dimension of C over C, what is that? This is 1. Okay? Dimension of C over C is 1. But whereas dimension of CC over C is 2, since dimension of C over R is 2. Okay? So that means, so what we are saying, the complexification of a, so I'm just think about it, that we are taking the same field but with respect to different fields, right, as a vector space. So we are considering C in two ways, as a vector space over real numbers, as a vector space over C, right? So looked C can be looked as a vector space over R and also as a vector space over C, right? Over C. Okay? Is it okay? So whenever you are considering C as a vector space over R, so look at this case. So its complexification is what? C over CC over C, having dimension 2, having complex dimension 2. Okay. Now we are considering C as a vector space over C. Now what is that? In that case, this is the complexification. Now C is actually a complexification. This is the complexification of the real vector space. R having dimension what? Having real dimension having real dimension 1. Okay? Okay? So that means we are having different objects out of this complexification motion, right? From the same field. Just looking at the same field in different fields, in different subfields. Okay. Okay. So what does this suggest? So this suggests us to think to us to view the complexification of the complexification of a complex vector space. The complexification of a complex vector space. complexification of a complex vector space V in a different way. Yes, as one doesn't know uh, as one does not know about the original, the given complex scaling on. Okay? Because because it will come in a different way. Okay? Uh, since it uses the real vector space structure of phi, and and, and every information every information uh, on multiplying a vector in V by I is gone. কারণ ওটা থাকছে না, যার জন্য তুমি ওই কমপ্লেক্স স্কেলিং সম্পর্কে কিছু জানতে পারছো, মানে কমপ্লেক্সিফিকেশন থেকে তুমি বুঝতে পারছো। Okay? Great. আমি এই পর্যন্ত নাকি? So let me check.